So good afternoon, and welcome to this session that I'm delivering on Game On with Azure Storage. My name's Alan Smith. I work as a developer for a company called Active Solution, based here in Stockholm. We've been focused a lot on building systems in .NET, and we've got quite a strong focus now on looking at the Azure technologies. We're seeing more and more interest in working and building solutions and starting to involve services and technologies that we've got available on the Azure platform. And we're seeing this sort of year on year increasing. There was a conference last week at Microsoft, the TechX Azure event, and there was probably twice as many speakers as there were the year before, twice as many sessions. So there's a lot of interest growing in these technologies. And what I'm going to be talking about in this session is one of what I describe as the core services of the Azure platform, looking at Azure Storage. Other core services is the service bus, something like websites, cloud services, Azure SQL database. And we're seeing so many projects where it's these services that are being used a lot during these projects. So the thing that's motivated me to start looking at this demonstration and putting this presentation together is the way that Xbox services like Xbox Live are starting to make use of cloud-based platforms. Not just the Xbox services, but Sony's PlayStation technologies. Also, all of the hands-on gaming that people are playing on mobile phone. All of the mobile games, mobile devices, running on iPhone, Windows Phone, tablet, and so on. Pretty much, these services are connected to some kind of a back-end system that's providing maybe authentication, maybe providing some in-game services. And many of them are monitoring what we call telemetry data, which is used in things like Candy Crush Saga to figure out how addictive the game is. It sends back stats on how people play the game in order to help to make it more addictive, make people want to buy more of those online game items. But one of the biggest customers for Azure is Xbox. They're currently talking, or they were a year ago, talking about spinning up 300,000 servers to actually run and host the Azure technologies. I've heard that it is getting close to this amount of servers per game on some of the actual live games that they're running. They're running something like 250,000 or 500,000 messages per second from the actual telemetry data from people playing the game, consuming vast amounts of resources in the Azure platform. When we typically talk about cloud computing, we're often talking about usage patterns, and these are sort of the four sort of common patterns that we think about when they're describing the cloud. We've got these kind of on-off events or one-off events, things like the Olympic Games, or for example, the website that we're running for this at this conference. It's going to get quite a lot of activity over a short space of time, but the rest of the time there's going to be not that much traffic on the site. We've got scenarios where we can use cloud computing for rapid growth, things like Twitter. They probably didn't know when they were developing Twitter that at the beginning of 2009 it was going to become incredibly popular. And you can see from the actual graph, the usage graph on Twitter, that they were doing a lot of firefighting with scalability and reacting to the demands that many more people are wanting to use the service. How can they increase the capacity and change the architecture? We've got some scenarios where the burst or the actual load on the system is very, very predictable. Formula1.com is an example. The Grand Prix for 2015 are already scheduled now, so we know when the Grand Prix are going to take place. You could basically draw this graph for 2015 about when there is going to be high demand on the actual website, based on last year's load and based on when the Grand Prix are going to be. Then we've got unpredictable burst. You can see from the bbc.co.uk graph, news.bbc.co.uk, the BBC News service is part of that website. And you can see the tsunami in Japan is the first big peak in 2011. And other peaks in 2011 are the Arab uprisings that were taking place, so the spring uprisings. So there's a lot of scenarios where these news events are going to cause rapid growth on systems. And I've been in a network control center where they actually had a TV on the wall showing a news channel with the sound turned down and with subtitles on. That's there for a reason. It's there because if they see unexpected network traffic, they can look up at the TV and see, is there some major news event that's breaking that's causing our servers to react. These news companies will need to react in minutes to sometimes a growth in 10 or 100 times of the actual load that's placed on the site. With online gaming, with the big blockbuster games that are being released, they kind of have a different growth curve that they have to be able to work with. And this is launch week. The game has to work on day one. All of the services have to work on day one. they've got very little opportunity to be able to load test their systems and analyze if their services are up to scale or not. If it doesn't work on day one, gamers are going to get angry. And you think when you're building systems for customers, customers can get disappointed if the service doesn't work. Gamers will start shouting and screaming and swearing, recording their thoughts on YouTube and broadcasting them to thousands and millions of people. So with these games, you really want to make sure that you are providing a good service for gamers. Over time, the actual demand on those services will decrease. Less people will play the game, less people will be playing Halo 4 when Halo 5 comes out, and people will move around to different games. So provisioning this architecture, it's not a case of buying in lots of servers to host this, because in a month's time, you may be going to be sitting at 50% capacity. It's a case of having a scalable platform where you can provision lots and lots of resources to be able to handle the load that's going to be placed on that game, and then gradually reduce the number of resources to be able to meet the demand. So Halo 4 is using some of the Xbox services and also using a lot of the services in Microsoft Azure platform. Things like game statistics, cheating and banning services. There's a lot of services that Halo is using. When the Azure platform was announced at PDC in October of 2008, this was kind of the amount of services that they were talking about. We had storage, we had web roles, worker roles, and a very basic way of being able to deploy applications to the cloud. About a year later, we got additions to those services. We got SQL database, we got the service bus, brokered messaging, and service bus capacities with queues and topics. We got SQL database coming along, and CDN and websites and virtual machines, durable virtual machines. And now when we look at Azure today, this is the amount of services that we've got available. So when you're choosing and building an Azure solution, one of the challenges is understanding all of these services, understanding which services are going to be useful to you, understanding the capabilities, the costs of these services. And very often, if you look at things like the Azure Storage queuing and the Service Bus queuing, you've got two services that do more or less the same thing. Analyzing and choosing which services to use can be a challenge. So Halo 4 is using the Service Bus. They're using the Service Bus Event Hub to do a lot of telemetry stuff. They're also using something called Orleans, which is an actor model implementation on the Microsoft platform. These services are available if you are building community games or handheld games, or if you're building games as a hobbyist, you can still leverage the same services that Halo is using. Because you pay for the usage, it's going to be very, very inexpensive to host your game using these services. And I'll talk about the costs of running a global event later on when we talk about the Azure pricing. So this is some of the services that we could use for games. What I'm going to be focusing on really is the blob storage and table storage capabilities. These were available when Azure was made public in October of 2008, and they're still available now. There's been quite a few changes in them, but still they're providing still the same core functionality that they did a number of years ago. So blob storage is a way of being able to store binary data, be able to store files. Many scenarios that we can use it for, and we'll look at those later on. Table storage is a way of being able to store billions of entities in a very scalable way and be able to store them in a non-relational data store. And I'll talk about the differences between relational data stores like SQL Server and non-relational data like table storage when we cover the table storage section. I left in the SQL Server slide. If you are going to be storing relational data in Azure, it's best to use a SQL database. That's what it's built for. One of the big mistakes when people start doing when they start to work with table storage is to take a relational database and then try to convert that relational database into a table storage. Save table storage for the vast amounts of data that is non-relational and use a SQL database for the actual stuff that is relational. Also, Project Orleans, I'm not going to talk about that much. I've been experimenting with it a bit, but it's definitely something worth looking at if you're interested in working with the actor model and looking at a new paradigm in storing and managing state of applications. I'm a big Formula 1 fan, and Formula 1 has been really driving an industry which is really, really a big business now. The industry surrounding the Internet of Things that you're bound to have heard of. What the Formula 1 teams have done is because they're so concerned about performance and the way that their cars perform as they're driving around the track, is they are really concerned about something called telemetry. Telemetry just basically means remote metering, and the Formula One cars will basically sample the data from the engines, the tyre pressures, the tyre temperatures. There's many, many readings that they take, hundreds of readings, and they take those readings hundreds of times a second. They can generate several terabytes of data, that's several terabytes of floating point numbers over a racing weekend, and being able to actually transmit and analyse that data is something that's going to be very important. Each car has one of these in it. This is an ECU, an engine control unit. These were developed by McLaren Electronics in the UK in partnership with Microsoft. Microsoft is also supplying a lot of the technology behind the telemetry systems used in Formula One. They're mostly based on SQL Server database. The ECUs, standardized in every car, will basically transmit the telemetry information to trackside so we can understand what's going on in the car. And this is telemetry data from Lewis Hamilton and Jensen Button a few years ago, showing the actual difference in the car speeds. It's really hard to see on that screen, but what it's highlighting is that Lewis's car was slower than Jensen's car going down the straight for some aerodynamic reason. And you can see, you can't really make it out, but there is things like the gear changes, the driver input, the speed, and all types of stuff. And that's just showing a few bits of the actual data that's captured. Microsoft is working in conjunction with the Lotus team to be able to help them to process and analyze this telemetry data. When I grew up watching Formula One in the 70s, every Formula One team was sponsored by a cigarette company. Today, pretty much every Formula One team has an IT company as one of their partners, one of their sponsors. It's not just the logo on the car, it's supplying all the back-end systems for processing this telemetry data. One thing about the technologies that they've been evolving with vehicle telemetry is that those technologies are starting to come down into regular automobiles. This is a great webcast that I recommend watching if you're into hobby development, Internet of Things, Raspberry Pi development. The guy in the video is a guy called Clemens Vastas. He's really the main sort of driving force behind the service bus. It was his idea to create the Azure service bus. He did a lot of the core development on it. And he's focusing a lot now on Microsoft's strategy for how Microsoft is going to develop systems to be able to handle the telemetry data that's coming from the Internet of Things. So this is what he's put in his car. He's got an actual connection which interfaces with the engine and the computer systems in the car. And this is a standard issue on each car. This is basically connecting to a USB device, and that's plugging into his Raspberry Pi. The power from the Raspberry Pi is coming from the power outlet or the cigarette outlet in the car. So when he turns the ignition on, the Raspberry Pi boots up and it starts sampling telemetry data from the car's engine. The Raspberry Pi has a wireless network card in, which is connected to the actual Wi-Fi that's in the car. His car's got a SIM card in it that can transmit data to the internet. So he's basically sampling his vehicle telemetry data and sending it into Azure. The data is stored in Azure Table Storage, so when he gets back, he can go into Excel, connect Excel directly to Table Storage, and this is showing a graph of his actual vehicle speed as he's driving. You can see here he's using a cruise control, and here he's driving slightly faster. This is in the Autobahn in Germany. You can't see that on the screen, but the speeds are going up to about 180 kilometers an hour, 160 kilometers an hour. So he's driving quite fast. There's no speed restrictions. You can see when he's hitting at roadworks and things like that. One of the reasons why this is going to be so useful for companies like taxi companies and vehicle delivery companies is the actual cost savings that we can make in fuel. Again, sorry that the slide isn't too visible on that screen, but it's saying you can basically get a 4% saving in fuel economy by keeping your engine properly tuned. By keeping the tyres properly inflated, you can get another 3% energy saving. A Raspberry Pi costs about 200 or 300 kronor, depending on the model that you purchase. And filling up the car with gas every couple of days, every day, if you're working in a commercial vehicle, is going to cost a lot more than that. So there's a lot of cost savings to be able to equip a fleet of vehicles with Raspberry Pis to be able to send telemetry data and analyze what's going in the car. It's going to be a good saving for companies, and it's very easy to do. Now we've got small devices, now we've got internet connectivity, and now we've got cloud-based services. The project that I'm going to be using for the demos is kind of a pet project called Red Dog Racing. Last year, I was developing a Pluralsight course on Azure Storage, and I wanted to have a demo that would work well when people are watching the videos of the course. So I basically downloaded an open source driving game for the XNA platform and started modifying the driving game to send telemetry data, lap time data, and replay data into Azure Storage, and using that as an example of what's going on in the course. Red Dog, incidentally, was the code name, or one of the code names for the Azure technologies before it was called Azure. And there's also Red Bull Racing, which is a Formula One team, so I've kind of put the two together to come up with that code name for the project. So I like working with the Azure technologies. I used to be a physics geek at school, so this kind of stuff interested me. There's a lot of physics in the driving game that I sometimes like to play around with. I like Formula One and I like driving games. So this is a great way of being able to sort of combine a lot of those interests and try and do something with Azure that's going to help to encourage people or be able to get people into using the actual systems. So what my focus is on is this bit, the kind of arrow in the middle, how we can get a game to integrate with services in Azure and how we can leverage those services to add some kind of online functionality to that game. This is what the overall architecture of Red Racing currently looks like. As I've mentioned, I've been working on this project for about 1.5 years now, and I keep making changes and adding things as new services keep emerging in the Azure platform, such as the Event Hub and the Streaming Analytics. I can then incorporate them into the game. So what I'm going to be focusing on really in this section is the storage section, how we can store the replay data in Blob storage and how we can store the lap times and telemetry data in table storage. We have a number of patterns when we're talking about the Internet of Things, telemetry, inquiries, commands and notifications. I'll run through those briefly. Telemetry, that's really what we're going to focus on. It's the timing data, the driver details, the sector times, the lap times of the lap, and these are going to be used to calculate who's in the overall lead of any competition that we're running, and also allow drivers to go and look how much faster or slower than they are than their competitors by going onto the website. Telemetry is really detailed information on how the driver is driving the car. So it will store the speed, the position, the acceleration, also the driver inputs such as the steering, how much the driver is pushing the gas pedal, how much the driver is braking. So they can go in and compare their lap with somebody else's lap and see if their friend is faster around the lap because they're braking harder going into certain corners. It allows you to analyze the performance of drivers. Inquiries, the high scores are scored in the game, and the actual game screen displays the high scores down the actual side when people are driving, and the high scores are updated when somebody else beats a lap time. So when the game starts up, it needs to call out to a web API service and get the actual lap times for the lap that we're driving on, so they can be actually displayed in the actual game itself, so you can see who you're competing against. It will also, once it's downloaded the best lap times, it will download the replay data from Blob storage, so it can actually have all of the other cars on the track, so you've got somebody to race against. Commands, I had implemented this, currently it's not implemented. I sometimes run this racing game as an actual workshop at conferences, so I've done this at DevSum, I've done this at NDC, where it's a full-day workshop. You start off with a racing game, and you basically work through labs, integrating the racing game with Azure Storage. So as soon as a developer gets hold of the source code for the racing game, one of the first things they're going to do is to decrease the weight on the car or increase the power on the engine. So the car can now drive at 500 kilometers an hour. So to prevent people from doing that, what I was doing was monitoring the actual telemetry feed. And if somebody exceeded the theoretical speed for the car, I would actually send a command to the driving game. And I would convert their 500 kilometers an hour of forward speed to 500 kilometers an hour of vertical up speed. So it was basically a way of being able to punish people for actually modifying the actual source code. Having said that, we didn't get too many people cheating in the actual workshops. People did actually play fair. Notifications, if another player beats a lap time and sets the highest score, we want to send a push notification out to all the people playing the game so that their actual time will get updated in the screen and you'll see who you're racing against. So I'm also implementing a push notification using the service bus in the game. So this is basically the architecture, a high-level view of what the game will look like. We've got a number of people playing the game, we've got a website, and we've got various services in Azure. The telemetry data is going onto the service bus. I've then got some worker roles that is dequeuing that data, putting it into the Azure Storage services, and we're using a website to be able to display this information. If you're building an Internet of Things project and you're thinking of using the Azure platform, this is probably what your architecture is going to look like. We've got various devices. They're going to be using maybe a Raspberry Pi or maybe some customized hardware to send messages out to the Azure service bus. Again, you're going to be processing that data, storing it in some kind of data store, and having a website that's able to actually display information based on that telemetry. So it's very similar architecture to what I've created in Red Dog Racing. A bit about the actual way we're storing data. We'll talk about the details in table storage, but we're storing the actual lap data to provide the scores on the actual website. The telemetry data gets sampled 10 times a second, and the messages are batched in once a second. So there's a lot more telemetry data than there is lap data. Looking at the way we actually store this data, as I've mentioned, we're using queues and worker roles to actually process that data. That's going into table storage. The website is displaying telemetry data, but we also want to be able to do a bit more detailed analysis on the telemetry data and show how drivers are driving around the laps. Now, when we think about storage, one of the options I could have chosen is, let's put this data in a regular SQL Server database. So I can go to SQL Azure, I can create a database, I can go into SQL Server Management Studio, I can start creating tables, or I can use Entity Framework, or I can use NHibernate, or I can use any of the other data access technologies. And this will allow me to start to build up a relational storage model. I can have a table for drivers. Each driver can have a driver ID, then they can have a name and various properties, and then each lap will be related to a driver. A driver drives a lap, so we've got the driver ID as a foreign key in the laps table, and that's basically linking on, and that's related to the drivers table. And this allows me to do things like this. Select the driver name, driver nationality, and lap time from the drivers, joining the laps joining on the laps table, and ordering by the actual lap time and the actual time when the actual time was set. And that will give me an actual result set there. Now, you're probably very, very familiar with this. How about doing this in non-relational storage? It's going to look something like this. I'm still going to have a table for drivers or competitors or locations or something like that that's going to store the people who are playing the game, details about that. But then I'm going to have a table for laps. Within table storage, and different non-relational storage systems work differently. We have a couple of properties. We have the partition key and the row key, and we'll be talking about those later on. You can see that the partition key for the drivers is the actual driver name, but the full driver name, I'm not using a driver abbreviation there. And then within the laps, I've got the partition key being the driver name. You can see that Alan Smith is appearing twice, Martin Belayu is appearing at 3 times. We've got the row key in there, and we've also got the actual lap time for the lap. Now, when we query against table storage, we're going to be doing a link query. This is one of the ways to query the data. If we're using .NET, if we're using the Azure Storage Client API, we're querying the data using links. So my query is going to look something like that. Get 10 lap times from the actual table where the driver name is equal to Alan Smith, or where the partition key is equal to Alan Smith. A couple of things about this query. There's no joins. We don't have the option to join. Also, and this is going to hit you when you start working with relational storage, there is no sort. I can't do an order by. So we do need to think about this when we're designing our storage. How are we going to query the data, and how is the data going to be ordered? So looking at creating tables in Azure Storage, I go log into the Azure portal when I've got an Azure account. I basically create something called a storage account. The storage account has a name, which is going to be globally unique, and that's going to be used in the URL to access all of the storage services. Within the storage account, I can start to generate tables, and I can generate as many tables as I want in there. Those tables are going to contain entities, and if we look at an example of that, the drivers table can contain Martin and Alan, the laps table can contain the data for all of the laps, but there's no relations between those two tables. Now, when we're working and programming in the Storage Client API, we've got a number of choices of how we access this data and show how we work to this data. It's not showing very clearly on the screen, so I'll see if I can actually jump in and show you this in code. So this is the actual code for the racing game. As I've mentioned, it is work in progress, so some of the stuff is checked out at the moment. In the actual storage section, we'll go and look at the telemetry and basically see how we're actually storing the telemetry data. So I've got a class here that's being used to access the telemetry data. I'm using various bits of the Azure SDK, the Azure Storage and the Azure Storage.table and the authentication. I'm working with a class called Cloud Table Client, which provides basically a client onto the tables. We've also got Blob tables and we've Blob clients, and we've also got Q clients. The Azure Storage's services themselves are all based on HTTP and REST. So you can use these services from any technology or any technology that can send and receive HTTP requests and understand XML or JSON formatting. As you know, any .NET developer, we get used to wrapper classes. So the storage API is just providing a wrapper around all of the storage services. But there's also you know, APIs in different technologies. You can access them using different technologies if you want. When Clemens was building his Raspberry Pi in the Audi, he was running on Linux. So he was using a different open source library to be able to actually communicate with the Azure services. He was using not .NET technologies there. The entities that we're storing in the table, this is basically what a table entity looks like. And in this example, I'm storing the telemetry data from a class which is called telemetry entity, and that basically derives from the table entity class. I always do this when I'm working with table storage. I always tell the user, or basically remind myself, what I'm using for partition key and what I'm using for row key. I'll talk about those choices a bit later on. And then I've got a bunch of public properties for the player name, the level, the car type, and then we get into the actual telemetry data itself, the position of the car, the direction of the car, the up vector of the car, and those three sets of coordinates can tell me exactly where the car is in 3D space. Then we've got the driver input, the steering input, the gear, throttle and brakes, whether you use KERS or whether you use DRS, KERS battery percent. And then quite a lot of stuff coming from the actual car physics engine. I'm putting in a lot more data in there than I'm actually using, because it's useful to be able to analyze and process this telemetry data a bit later on. So I want to put a lot of stuff in there. So the telemetry data basically looks like this if we go to one of the telemetry tables. I think I've got that, maybe not on my dev storage account, but maybe in the cloud storage account. So this is the telemetry data back from when I was running the workshop at NDC. The data is basically stored in there, in that format. So one of the things that we really need to do when we start to talk about working with table storage is to abandon the concept of thinking about rows and columns. And it's really challenging to do because of the way that this data is stored. It looks like a data table. The way it is displayed basically makes us think that these are rows and columns. The table storage table contains entities, and the entities have properties. The entities in a table storage table can have up to 256 properties. 3 of them are reserved, the partition key, the row key, and the timestamp. These are reserved properties. But the other ones, you can basically add as many properties. You can add up to 256 total, so there's 252 that you can add additionally. Each entity in the table can have different properties. You don't have to have the same properties per entity. This makes it confusing when you're using this tool to query the entities, because you'll see what you would think of being columns with empty values, and it basically looks like they've got a load of null values or missing values there. But remember that these are not columns, and these are not rows, they're entities with properties. Some entities may have more properties than others. This becomes slightly more apparent when we look at the lap time data. So if I look at player lap times 0, or the actual ranking lap times, that's a good example. There's 3 different tracks in the driving game. There's track 0, track 1, and track 2. The tracks are different lengths, and therefore the tracks have different numbers of sector times. So if I zoom along here, you can see that the first track, track 0, has 8 sectors in it. The sectors are every 500 meters in the track and roughly every 10 seconds apart in driving games. But as we scroll down, some of the actual track data have more sectors in them. And this is an example of using the entities and properties. I can, theoretically add a really long track in the driving game that has 100 sectors that's, 50 kilometers long, and table storage will handle it. It won't mean that the track 0 has a null value for sector 9, 10, and 11, and so on. It'll just mean that those properties don't exist. If you're working with very dynamic properties like that, there is another class that we can use for table storage access, which is the dynamic table entity. If we go into the lap data table and look at the operations that I'm performing against that, I'm not generating a class that represents lap data. I'm using a class which is called dynamic table entity. So I'll see if I can find some examples of this. Yeah, this is basically the actual class that I'm using. The dynamic table entity is basically created, and then we set and assign various properties to it. So I'll see if I can, yeah, this looks like it's... yeah, this is it. I create my dynamic table entity, and then I've got the option of adding a number of properties to this. So I'm creating this, which is called my sector times entity. I'm calling sector times entity.properties.add, and then I can just basically add whatever properties I want to, and I specify, what type I'm generating based on the actual type that we're using there. And you can see when I'm adding the actual sector data, I can just basically loop through however many sectors we've got in there and just add properties onto that entity and then push it into table storage. So that's basically how we're actually working with the actual classes there. When it comes to these reserved properties, the partition key, the row key, the timestamp, and the e-tag, the two that we're going to be most interested in is the partition key and the row key. The timestamp it can be useful. That basically tells you when the entity was last updated in table storage. It's something that's set by the system. The e-tag is used to implement the optimistic concurrency that we've got implemented in table storage. And that's not actually stored in table storage. It's generated when we retrieve an entity and used to basically work with optimistic concurrency when we store the entity there. Optimizing the queries, when you think about querying the data, we need to know a bit about the way that queries are optimized. The most optimal way of being able to retrieve an entity from table storage is to specify the partition key and the row key of that entity and just do a retrieve operation like that. The partition key and the row key have to be unique within the same table. You can't have any duplicates there. But you could have a table with a billion entities in it, and you could say, give me this particular entity, and your query would come back in probably under 100 milliseconds if you're actually in the cloud platform. It would be a very, very quick query to execute. Another quick query that we can do, if the partition sizes are fairly small, is select all of the entities within a partition. So if I had decided to use the driver name as a partition, I could say get all the laps where the driver name is equal to Alan Smith, and that will basically query through, and that will be an efficient query. In this scenario, I'm using the actual track name as the partition key. So I can basically go in and say, give me all the lap times for track 0, give me all the lap times for track 1. Range queries can also be fairly optimal. I'm basically selecting within a partition, but I'm selecting a range of row keys, starting at this and ending at this. So those range queries can be useful. And these are all because we know exactly where to actually retrieve that data from. When it starts to get inefficient is when we do this. We start to query for the actual driver name. The driver name is in that column over there, but it's not the partition key or the row key. Ever since table storage came out, Azure developers have been asking the Microsoft team to add something called secondary indexes to table storage. It's something we've been campaigning for years. It hasn't happened. I don't know if it ever will happen, but it's something that is always on the to-do list for the Azure Table Storage team to add secondary indexes. If they did, I would be able to drop a secondary index on the player name, and then it would be efficient for me to query that. So when I end up working with a racing game, I end up generating multiple tables in Azure Table Storage. If we actually look at what I'm storing the data multiple times. And this becomes apparent when we're going to be looking at the lab that we're doing for the Global Azure Bootcamp, which I'll talk about a bit later on. So I think this is the Global Azure Bootcamp test. If we look in the tables there, I've got something called the ranking lap times. This is showing me for each track the actual top lap times that we've got on that particular track. So going in, you can see that we've got this partition key being track 0. I'm selecting based on the track. We've got another table which is based on track 0, based on the actual country where the driver is on. So if I want to get the top drivers for a specific country, I can actually run this query here. I don't know if there's any other countries here appearing in here. So there should be some more. You can see here we've got SE, the actual country code. GAB is the actual country code for the Global Azure Bootcamp organisers here. SE, that's for Sweden. And this allows me to query by partitions key and say, okay, give me the laps for Sweden if I want to do a page for Sweden. Then I've got the actual location tracks. Each Global Azure Bootcamp location is going to have its own location ID. So what I can do then is say, okay, give me all of the lap times where the location ID is equal to 1011, which is a location ID for Stockholm, Sweden, and the data will be returned for that. So because of the limitation that we've got in querying the data, sometimes we have to insert duplicate data into table storage and have multiple copies of that data. It can be a challenge to keep that synchronized, but in my scenario, once the lap time is set, that lap time is not going to change. That's going to stay there permanently. So it's fine to do that. When we look at the costs of Azure Storage, you'll realize that it's not a big deal to do this. Unless you've got billions and billions of data or terabytes and terabytes of data, it's not going to be a very expensive thing to do. We also need to understand a bit about how the data is ordered and how we're actually going to get sorted indexes coming back. The entities in a table are ordered and grouped by the partition key, and the partition key is a string, and it's not going to understand anything about Swedish letters. You're not going to be able to set a Swedish search order on the actual tables there. So that allows us, for the tracks to be able to have them sorted by tracks. That's not really the most useful one, but the useful thing is here that within a partition, entities are ordered by the row key. Now this is where we start to get around the limitation that I can't do order by in this. What I'm showing here is the actual row keys, which is a string value, and if I zoom in on the actual screen there, what we should be able to see is that the row keys all begin with numeric values. These are actually strings, so I've zero padded the numbers on the strings just to so alphabetically it will be ordered correctly. And you can see that the first entry is basically 000560078, then we've got 000562771. If we look at the lap time in milliseconds, you can see that the lap time in milliseconds for the top lap is 56078, 56.078 seconds. And then we've got 56.271, 56.333. And because I'd actually set that row key to be a zero padded based on the actual lap time, that's basically showing me the actual correct order for the lap. So when a new lap is inserted, if it has beaten the other times, the row key will be alphanumerically sorted, appearing at the top of the list. So when I actually query, I just basically say, give me the top 10 lap times from that table, and they will be basically sorted correctly for the actual website. If I decide to sort by the number of crashes that somebody had on a lap, who crashed the most or who crashed the least, what I'm going to have to do is to retrieve all of the laps, get them into memory, and then actually start to sort the list in memory to actually sort for the crashes. So then again, I'd start thinking about, okay, let's generate another table for the crashes and store those in that particular order. And then if I want to do that for every country and every region, you get the picture. There's going to be a lot of tables in there. So it can be challenging to get the data out. Had I chosen to go for a SQL Server database, I could run these queries fairly easily and just do order by this, order by that, and I should be able to get fairly reasonable performance, unless I've got millions and millions of entities in there. The table storage design strategy. What I'm really interested in is having various tables on the website. I think I can actually show you the website here. I should be able to zoom in on this and make it a bit more readable. This is the actual reddog.azurewebsites.net. This is probably the prototype for the site that we're going to be using for the Global Azure Bootcamp. And you can see here the various tables that we've got. When I go into beginner lap times, I want to be able to see who's fastest in the particular locations. This is coming from test data, by the way. So, I mean, I've been testing this a lot. I think Martin Blyer also tested it. Mike Wood tested it, but he's self-confesses that he's not too great at playing driving games there. And you can see all of the lap times here, and they're sorted in that order because of the way that the table storage works. You can see the same for the advanced track. You can see the same for the expert times. What we're going to be doing, hopefully, if we can pull this off, is to make the data in table storage accessible to the public. So when you go to a global Azure Bootcamp location, if you're in Stockholm, Sweden, you can actually build an Azure website for the data in Sweden, query off those Swedish tables, and you'll be able to have your actual location, just selecting the people at your location and having that high score table for your actual location. So that's something that we probably will be focusing on. Another thing as well is achievements. I'm storing achievements in there for people who do certain things in the game, like with the Xbox, and this is going to allow the countries to compete with each other for getting the achievements. So I've just been experimenting with these. There's going to be a total carnage achievement if you crash a lot during a lap, a clean lap achievement, fast times on the different track achievements there. So people will be able to get those achievements during there. And also, again, I'm using table storage for the achievements there. And this is just test data. Partition key is the actual country, and then we've got the row key being the actual name of the achievement, and all these properties as to which driver got the bronze achievement, which location got the bronze achievement, and so on. And I'm just experimenting with that data currently at the moment. The telemetry data, there's going to be a lot more of that than there is lap data. This is going to be used to allow us to click on the website and see how the drivers have been driving, and that's kind of a basic telemetry graph which is showing the speed of the car, which is typical in a driving game. You accelerate to full speed, drive a lot, and then you come to a corner and you crash at the corner. You accelerate to full speed, hit another corner and crash. So that's basically what the telemetry looks like for people who are new to the racing game. If you're driving better, a better driver, you would actually see that the speed wouldn't go down like that. It would tail off because you'd be able to see the driver braking and see some actual input from the brakes. So comparing a fast driver's lap time with a slow driver's lap time is going to allow you to analyze, how drivers should drive around the lap responsibly. This is another view on the telemetry data that I've been experimenting with, and what this is allowing us to do is to go in and analyze hundreds of laps in the driving game and see how players are actually driving. What I haven't shown here is I haven't actually drawn the track. This is the actual positions of the cars. It's very challenging to see, but the lines are red where the actual cars are driving slower and green where the cars are driving faster. And you enter the section here, so everybody's going fast. What I'm showing, the red dots, this is where crashes occurred during the lap. So you can see on particular corners in the driving game where most people will crash if they're driving too fast. So a few people are crashing on the inside of this particular corner, but it's at the outside of that corner where most people are crashing during the driving game. So this data could be used in a real world situation. Hopefully it wouldn't look like that, but analysing where accidents can occur in the road is something that's going to be very useful. In the driving game, being able to, for people to see this and say, okay, this is where you need to brake, you need to be travelling at a certain speed at this particular section of the course if you've got a good chance of being able to get around that corner. It's going to allow people to improve their driving skills. So the telemetry data that I'm storing a lot of this telemetry data, and the way that I'm storing the telemetry data, I'm using the, I've covered the lap time stuff. The telemetry data, I'm using the actual lap ID as the partition key, and then the actual car's position on the track. I think I've changed. I think I'm actually using the milliseconds game time in the actual game as the actual row key. So when we select telemetry data, there's really a couple of scenarios when we're going to be querying that data. The first one is, give me all of the telemetry data for a particular lap. And that's going to allow the website, when you click on the lap time, to show how that driver has driven that particular lap. So that's an efficient query, is give me all the entities where the partition key is equal to that. The other type of query that we can do is sector analysis for multiple laps. So this is saying, okay, let's look at the top 100 laps. From each of the top 100 laps, let's go out and query onto table storage, and let's select where the row key is between this value and this value. And that's going to give me that particular section of the lap that then I can draw on the graph. And we can actually run that as a fan-out query in parallel. So retrieving that data, if we're doing 100 queries, may be a bit slow to put on the actual website, but it's going to allow us, for analysis purposes, to be able to generate these analysis reports fairly easily. So all the time with table storage, we are focusing on how we can query that data and how we can analyze that data. What's going to be the most efficient way to query that data? The next service I'm going to talk about is Blob Storage. I love Blob Storage. I think it's one of the most useful services that we've got in Azure. How many people have got MSDN accounts with some kind of subscription? How many people have actually activated the Azure benefits that you get? And how many people are effectively using their $100 or $150 worth of usage to be able to back up stuff at home? Virtually nobody's doing it. When you look at the cost of Azure, you can store a lot of stuff in there, and it is stored very securely. It's also very reliably. Anything that you put in Blob Storage by default is stored on 3 physical locations in one data center, and it's also replicated to 3 physical storage devices in another data center. So even if one of the data centers catches fire and burns down, you should still have your data because of the geo replication. It's incredibly inexpensive to use, incredibly flexible as well. So many of the projects that we work on using Blob Storage, I'd say a lot more than using a table storage. So you can use it for documents, images, videos, log files, all kinds of stuff. Same with the accounts. You basically create a storage account. You can then create blob containers within that. I'm using it currently for my website, cloudcast.net. I've got a blob container for photos and a blob container for videos, and I can basically generate JPEG files in the photo that are used on the website, and I can then upload videos and webcasts into the video section of the blob storage and basically play those on the website. So it's a great way of being able to actually store data in there. One of the scenarios you can use this for is website content. I said probably about 10-15 minutes ago that the Azure storage services are based on a REST API. We can also make the blobs public, meaning that if we send an HTTP GET request to the blob storage location, it will return the content of the blob. We can also specify in the blob storage what the actual content type is, what the MIME type is. So we can say, this actual blob of data is a JPEG image, and we can make that public. Now, when the browser makes an HTTP request to that actual blob location, it will basically return the image data, and the browser will understand that it's an image, and it will display it in the website. So instead of storing stuff on IIS or in Azure websites, you can really reduce the size of the deployment packages that you're sending into Azure by putting lots of image data or binary data or site content out into blob storage and making that public. You can also update this blob storage content without having to actually update or redeploy the website. So it makes it very flexible when working with websites. Better still, Blob Storage also supports something which is called CDN, Content Delivery Network. So if you've got a site that people are accessing around the world, like we're going to be doing for the Global Azure Bootcamp, if you turn on the CDN functionality, I think there's about 40 data centers around the world which are known as CDN edge nodes. So if somebody is in South America and they access your website that is hosted in Amsterdam or Dublin, one of the European data centers, the images will be pushed across to South America, to the closest data center that we've got as far as latency is concerned. The next person that accesses your website in South America will basically get the image from that local data center. So the latency and the speed of your website will be much, much better just by switching on the CDN functionality. And really, CDN is something that is very, very challenging to do on your own. It's something that Microsoft can provide just as a switch that you can put onto the blob storage. Yeah. Okay, another scenario is photo backup. This is what I do at home. I've basically got a home PC, I've got a work PC. I can basically synchronize my photos and push them all up into blob storage. It's so inexpensive to do this, and it's a really easy way of being able to actually replicate data between machines. Instead of using SkyDrive, instead of using Dropbox, you can basically use blob storage to do that. You have to write a bit of code to do it, but it's a more secure and more reliable way of being able to do it than using these actual storage services. The scenario that I'm using is storing the actual replay data for the ghost cars. The original XNA game, XNA racer game that you could download, basically had a replay functionality. And what it would do, it could run on the Xbox 360 or it could run on Windows, is when you completed a lap, if you had beaten the the best lap time in the game, it would basically save down the actual replay data onto the storage device, which would be the hard drive of a PC, or it did also interface with the Xbox 360 storage devices. So when you were playing the game, you'd be racing against the ghost car from the fastest player. So I thought, how hard is it going to be to modify this to actually store the data into Blob storage? And it was incredibly easy to do this. It's a data stream. I put in about 4 or 5 lines of code into the game, and it now basically stores the lap data into Blob storage using the actual lap ID and the track name to actually store that data. So if we go into Blob containers, gab test replace, and I just zoom in on this. What you see here is the actual blobs, the binary data for each of these replays. So this is basically the track that we're on and the actual lap ID. So that can be retrieved fairly easily when you're actually playing the game there. And we can actually hopefully see the size for that if I scroll along here. Between sort of 35, 40, sometimes 20 meg of data, depending on how many samples we've taken. So there's not a lot of data in there. So if we see how that looks in the game and just run this, what I'm going to have to do is authenticate myself as one of the global Azure Bootcamp locations. And hopefully I'll try not to show you what that authentication code is. I think I'll need to have my game services running. I'm trying to run this in a mixture of a local website and using local storage and using the actual shared storage. So what I'll need to do is to put in a location key. Hopefully that will have it. And now we've authenticated into the game. And if I just basically wait and do nothing, there is kind of an actual timeout which goes to the display screen. And this is something I've talked about doing mods for the game. When I was traveling to a conference, I think I was stuck at an airport, and I basically started putting in all of these camera positions around the track. So what we're seeing is the actual top lap times, which are shown in this display down the side of the screen there. You can see the various flags. And we're getting the actual ghost cars for these top lap times and putting them in the track racing against each other. It's a bit hard to see, I keep saying that, but the actual cars do have the actual flags of the nations mapped on as textures there. So you can see different cars driving around the corners and overtaking each other. So it should be fun and really help to build on the sort of community feel that we've got running in the Global Azure Bootcamp. I'll see if I can drive a lap. And select this, and what we should see is as I start driving, we'll see all of the ghost cars for the different regions appearing there, and you can basically go around racing. I've been modding the code and I have put this in, so if you drop behind the cars, they basically do change into cars with the actual flags on them, but that's really confusing when you get in amongst them, so they do actually drop into the actual ghost rendering, the transparent rendering, when you get fairly close to them. Again, this is something that I'm experimenting with, so it's going to be probably different on the day, something that we're working on there. Okay, we do have some limits on these storage services. We also do with the table storage. But basically with Blob storage, once you've created a storage account, you can store 500 terabytes of data in that storage account. And then you can generate, I think you can now generate 100 storage accounts in an Azure subscription. So that's 50 petabytes of data that you can store in one Azure subscription. That's a lot of stuff. It is going to scale to give you the storage capacity that you need. There are some maximum blob sizes, 200 megabytes for block blobs, 1 terabyte for page blobs. I haven't really talked about the differences between those two blobs. And you can partition data between those at those two different scenarios. There are some limitations on the actual throughput, but it does provide fantastic performance on accessing this data. Hopefully for many scenarios it should be well within limits. Microsoft is also previewing something called Premium Access Storage, where you can pay quite a bit more money and you will get these actual limits far exceeded. It will give you much better performance, fantastic performance, but there is a price to pay for having a premium storage capacities. So I think I've covered that section. A bit about the Global Azure Bootcamp. We're currently, when I checked this morning, 89 confirmed events and 20 pending. We've got 2 scheduled for Stockholm. Last year we had 138. The year before that we were about 98. So we're hoping that maybe we can get at 200 at locations. So how much is it going to cost to use storage services for telemetry and lap time processing for the Global Azure Bootcamp? And I put this cost estimate together this morning. If we have 200 locations, which we may do, if we have 2,000 players, which is 10 players per location, Very often with the past Global Azure labs, we've had scenarios where there's a language barrier in communicating with people at those actual locations. So many of the labs that we've done, the global labs, a location hasn't actually competed in the lab because they didn't get the information in the appropriate language. So we may not see 2,000 players, we may see more. I've just made a guess at that. If each player drives 10 laps, they may or they may not do that. Some players may drive more, many players may drive less. Then we'll get 20,000 laps, but that's my estimate. The total amount of storage that I would guess that we would use for storing the replay data for 20,000 laps is 0.76 gigabytes. The actual lap data, we store one entity in the table, or maybe sort of 3 or 4 entities if you're using multiple tables per lap. There's going to be not that much data there. For telemetry, there's going to be quite a bit more because we're storing maybe up to 800 or 1,000 or 2,000 entities in the table for the actual telemetry data, and there's a lot of telemetry data, a lot of different values there. That's going to be probably about 5 gigabytes. Also, we get billed for transactions on storage. I guess that we will run about 2.5 million transactions against table storage through the day, and also we get billed for data leaving the data center. 3.2 gigabytes is what I've guessed. So anybody want to guess how much this is going to cost? I had to run through these figures several times just to make sure that I'd got that correct. I'm calculating on how much it would cost to store that actual data for 1 month, which is 2.5 Swedish kronor. The storage transactions came out to 0.65 Swedish krona. The data egress, it's free for the first 5 gigabytes per month. So the total cost I'm estimating for the Global Azure Bootcamp is going to be a little over 3 krona to actually store that data in storage. You need to start using this stuff because this is just so cost effective. Think about building a mobile game that's going to scale to 1 million players. And if it's going to be costing you, a few hundred krona or a few thousand krona per month, you're going to have massive reach, massive capabilities for being able to work with this. Think about a scenario where you're harvesting lots of telemetry data. Typically, storing that telemetry data is the challenge. Buying a SQL server, buying a data store, buying an on-premise file storage system is going to cost you thousands and thousands of dollars. Being able to actually leverage something that costs you 0 from day one, and the costs are going to actually increase as you start using that storage more, is going to be a lot more cost effective. So this is definitely a technology that many projects are going to be using. Also, these prices are dropping because Amazon have their own storage system, Google have their own storage system, and they keep undercutting each other's in cost. So it's basically going to be getting cheaper as we go on and advance and the cloud platforms evolve. Thanks very much for listening to my session. I'd also like to say a big thanks to the Swedish .NET developer community for putting on this event. I've had some experience of doing the Cloudburst conference, and it's a brave thing to do, and I'm glad that you pulled it off and it's been so successful. My name's Alan Smith. Thank you very much.